In this Java tutorial, you'll learn about inheritance, polymorphism, and constructors. The first 4 topics we'll cover are how methods are inherited and how to use inherited methods. Next, we'll cover polymorphism. Finally, we'll learn how to write constructors in both standalone classes and classes that are part of a hierarchy. In this first lesson on inheritance in Java, you'll learn how methods are inherited by subclasses from their superclasses. Important facts about inheriting methods. A class that inherits is called a subclass. In this diagram, tiger is a subclass of animal. A class that is inherited from is called a superclass. Animal is a superclass of tiger. Subclasses are in an is-a relationship with their superclass. We can say tiger is a animal. A Java class can have many subclasses, but only one superclass. In this updated diagram, both tiger and bear are subclasses of animal. Anything with a private modifier, like a field or method, is not inherited, but can be indirectly accessed from a subclass. Here we have an example of a worker class. The worker class does not explicitly extend anything, so it is not explicitly a subclass. However, it implicitly extends object, so it is a subclass of the Java object class. The extends keyword is how we tell Java that the class we are writing is a subclass of another class. Any class where we don't explicitly use the extends keyword implicitly becomes a subclass of the Java object class. Worker has 2 methods. DoWork is a public method, which means 1, it will be inherited by subclasses, and 2, it can be directly accessed from other classes. Earn minimum wage is a private method, which means 1, it will not be inherited by subclasses, and 2, it can't be directly accessed from other classes. Our next class is tradesperson. Tradesperson is a subclass of worker. Tradesperson inherits DoWork, but will not inherit the private earn minimum wage. Additionally, tradesperson will add a new method, DoSkilledWork. Our third class is carpenter. Carpenter is a subclass of tradesperson. Carpenter will indirectly inherit DoWork, directly inherit DoSkilledWork, and add its own method, DoWoodwork. To clarify the relationships, worker is a object, tradesperson is a worker, carpenter is a tradesperson. Let's look at a new class, worksite. Worksite is not in an inheritance relationship with worker, tradesperson, or carpenter. We've declared a worker variable, Alex, and initialized it with a new instance of the worker class. If we tried to call alex.earnMinimumWage from the worksite class, we'd get an error. Earn minimum wage is private, so it can only be called from another method inside the worker class. However, we can call DoWork from Alex. Indirectly, we are calling the private method earn minimum wage, which is okay because the actual call happens inside the worker class. The output will be does unskilled work and earns minimum wage. Let's look at the next class, worksite2. We've got worker Alex initialized as a new worker. Tradesperson Barbara initialized as a new tradesperson. Carpenter Carol initialized as a new carpenter. For Alex, calling DoWork is legal because DoWork is public and thus accessible in the worksite2 class. For Barbara, calling DoWork is also legal because the method is directly inherited. For Carol, calling DoWork is legal because the method is indirectly inherited. Let's look at a final class, worksite3. Again, Alex is a worker, Barbara is a tradesperson, and Carol is a carpenter. It is illegal for the Alex variable, which is pointing at a worker object, to call the DoWoodwork method. Superclasses can't inherit from subclasses, so a worker object can't access the DoWoodwork method in the carpenter class. For the same reason, Barbara, which points at a tradesperson object, also can't access the DoWoodwork method. The Carol variable points at an instance of carpenter, so it can call the DoWoodwork method. Next, we're going to learn about overriding methods. 4 important things to know about overriding. Overriding replaces a method instead of inheriting it from the superclass. Only non-static methods can be overridden. There is something similar called hiding that can be done with static methods, though we won't discuss it here. Private methods can't be truly overridden, though they can be replaced. Let's look at alternate versions of the worker, tradesperson, and carpenter classes. In worker, the DoWork method is public, so it could be overridden in a subclass. If we don't override it, it would simply be inherited. For security reasons, earn wage is private. We don't want programmers to be able to call it directly from outside worker because they could create a payday without doing any work. Being private, it will not be inherited to a subclass. In tradesperson, we've overridden do work, so it behaves more appropriately for a tradesperson. The override annotation is optional, but it's a good practice. We've created a new method to handle the payment called earn union wage. In carpenter, we again override do work. If we hadn't overridden do work, carpenter would have inherited the do work from tradesperson. Again, we created a unique payment method, this time called earn carpenter's wage. Let's look at the diagram of class relationships. Worker is implicitly a subclass of object, tradesperson is a subclass of worker, carpenter is a subclass of tradesperson. Let's look at this unrelated class worksite. The main method will execute from top to bottom, but we're going to jump around a bit to focus on one variable at a time. We start by declaring a variable, Albert, of type worker, then initializing it with a new instance of the worker class. Let's skip down a few lines to where we call the doWork method from the Albert variable. This method outputs does unskilled work. Next, the method calls another method, earnWage. EarnWage is private, but since the call comes from inside the same class, this is legal. The earnWage method outputs earns minimum wage. Next, let's look at tradesperson. The Bob variable is pointing at a new tradesperson object. We skip down and call doWork from the object that the Bob variable is pointing at. Java goes to the overridden version of doWork, which outputs doSkilledWork. Then it calls the earnUnionWage method, which outputs earns union wage. Finally, the carpenter variable Cynthia, which is initialized to a new carpenter object. Later, we call the doWork method from the Cynthia variable. Java goes to the overridden version of doWork and outputs does woodwork. Then it calls the method earnCarpenterWage, which outputs earns carpenter's wage. Remember, if we do not override a public method in a subclass, the most recent version of it will be inherited from a superclass. Next, we're going to talk about using the super keyword to call methods in a superclass. Some important facts about using the super keyword. We can use the super keyword to call methods in a superclass that have been overridden in the subclass. Super can also be used in a constructor to call a constructor in the superclass. We won't learn about this second use right now. We have two sample classes. The first is the car class. Here, we define the method applyBrakes, and here we define the method checkSurroundings. The second class, self-driving car, is a subclass of car. Here, instead of inheriting applyBrakes from car, we override it. And here, instead of inheriting checkSurroundings from car, we override it. Emergency override is a new method unique to self-driving car. Inside the emergency override method, there is a call to super.applyBrakes. This is instructing Java to call the applyBrakes method from the superclass car, even if there is an overridden version of the method in the self-driving car class. We're going to look at three different method calls. The three examples may feel a bit redundant, but it's important to understand how the rules apply in each circumstance. Now let's add a new class highway. Highway isn't in an inheritance relationship with either car or self-driving car. In highway's main method, we create a variable called Ford Mustang and initialize it with a new instance of the car class. Next, we create a variable called kit and initialize it with a new instance of the self-driving car class. Finally, we call the method applyBrakes from the variable Ford Mustang. Ford Mustang is pointing at a car object, so we don't even need to think about the self-driving car class. We call applyBrakes. It outputs driver applies brakes. It calls another method, checkSurroundings. It outputs driver checks surroundings, and the program completes. Let's look at the country road class. The first two lines in the main method are the same. We declare and initialize the Ford Mustang and kit variables. This time, on the third line, we call applyBrakes from the kit variable. We have two possible applyBrake methods we might call. Looking back at the earlier code, we see that kit is pointing at a self-driving car object, so we'll use the most recent version of that method, which is in the self-driving car class. Java outputs computer applies brakes. Next, the method calls another method, checkSurroundings. Again, there are two different versions of the called method. Since kit points at a self-driving car object, we'll use the most recent version of checkSurroundings, which is in the self-driving car class. Java outputs computer checks surroundings, and the program completes. Let's look at a third example. Again, we have the variables Ford Mustang and kit. Here we call emergency override from kit. The emergency override call is unique to the self-driving car class. First, Java outputs driver takes control. Next, there is a call to super.applyBrakes. Kit is pointing at a self-driving car object, but super means we want to call the applyBrakes method in the superclass car. Java outputs driver applies brakes. Next, a call to checkSurroundings. This frequently confuses programmers because they assume since they are already up in the superclass car, they'll stay there and use car's version of checkSurroundings. However, let's use the same criteria that we used in the last two examples. Kit is pointing at a self-driving car object, so we're going to use the most recent version of checkSurroundings. That version is in the self-driving car class. Java outputs computer checkSurroundings, and the program completes. There's two important things to remember. First, in this context, super specifically looks in the superclass to call a method. Second, by default, Java uses the most recently overridden version of a method based on the object type. Next, we're going to talk about accessing private fields in a superclass. Two important facts to know. We cannot directly access the private fields in a superclass from a subclass. We can, however, indirectly access them if there are getter and setter methods in the superclass. Let's take a look at these two classes here, animal and bird. Animal has a private field, num of legs. Since num of legs is private, it can't be inherited to a subclass and can't be accessed outside the animal class. In our subclass bird, we have another private field, feather color, which wouldn't be inherited to a subclass of bird and can't be accessed outside the bird class. We have a method in the bird class, reportStats. Let's look at it line by line. First, we output the value of the feather color variable. Feather color is private, but we can still access it from a method inside the bird class. On the next line, we output the value of the num of legs variable. Being private, it isn't inherited, thus isn't accessible to the methods inside the bird class. Let's see what we can do to make this work. First, we're going to make some changes to the animal class. We create public getter and setter methods. These public methods are inherited to bird and thus accessible to methods inside the bird class. Back in the bird class, the reportStats method still can't directly access the num of legs variable. We replace the variable name with a call to the getter method to retrieve the value of the num of legs field. Remember, just because a private method or field isn't inherited doesn't mean it's not there. Private fields or methods in the animal class are still part of a bird object. They just aren't accessible from bird methods. However, sometimes programmers give us other methods to indirectly access those private fields and methods. Next, we'll learn about polymorphism. Some important things to know about polymorphism. Reference variables, such as the Athena variable here, can point to an object of the same class. Athena, a variable of type animal, is pointing at a new animal object. Or an object of a subclass. The Simba variable of type animal is pointing at a new lion object. If a variable is pointing at an object of a subclass, only methods that exist in the variables class will be available. We'll talk more about this later. Let's look at this hierarchy of classes. For our purposes, let's assume all the methods in these classes are public and non-static. We have animal at the top, then animal has two subclasses, mammal and reptile. Mammal has two subclasses, lion and bat. Reptile has one subclass, dragon. In some cases, we'll be adding new methods to the subclasses. In other cases, we'll be overriding methods from superclasses. Let's write some code. We declare a variable Alex of type animal. Since Alex is an animal type variable, it can point to an object of either animal or any of animal's subclasses. Here we have Alex point at a new instance of the lion class. Let's think about which methods the Alex variable can access. Alex is an animal variable, so it can access any methods that originate in animal. We may have overridden those methods in Lion, but as long as they exist in Animal, they will be accessible by the Alex variable. Let's look at the Animal class. Animal contains the methods eat and sleep, so both methods will be accessible from the Alex variable. Next, let's look at Mammal. Mammal adds the control temp method, which will be inherited by Lion. However, since there is no control temp method in the Animal class, it will not be accessible through the Alex variable. In the Lion class, we override the sleep method. Since there is a sleep method in the Animal class, we can access the overridden method from the Alex variable. The roar method is unique to the Lion class. Since there is no roar in the Animal class, we can't access it from the Alex variable because Alex is an animal type variable. Let's write some more code. We call the eat method from the Alex variable. The Lion object runs the eat method that is inherited from Animal. Next, we call alex.sleep. The variable type, in this case Animal, determines which methods we can run. Since the Animal class contains the sleep method, it is accessible from Alex. The object type, in this case Lion, determines which version of the method is run. Java runs the version of sleep that was overridden in the Lion class. Finally, we call alex.controlTemp. While the method exists in the Lion object, we can't call it from the Alex variable, so it generates an error. If we change the Alex variable to either a Mammal type or a Lion type, the call to control temp would be legal. At this point, people usually ask, why wouldn't I always just declare Alex as a Lion and have access to all the methods? In this example, you probably would, but I'm going to show you two examples where polymorphism is useful. Here, we create an array of animal called zoo. Perhaps zoo is a list of all the enclosures available, and we can populate each with an animal. We initialize index 0 with a lion, index 1 with a reptile, and index 2 with a bat. Now let's go back to our hierarchy. Later on, the zoo acquires an alligator, and their programmer writes a new class for it. We can simply initialize index 3 as an alligator without changing anything else. Let's look at another example. Here we have a zoo class with a lion, Kitty, and a dragon, Sparky, in the main method. We also have a veterinarian class. The veterinarian class has a diagnose method that can take in any animal or animal subclass and return a diagnosis. This is powerful because instead of having a different method for each type of animal, we can pass in any animal to this one method and get a diagnosis. Here's an example of how we could pass Kitty and Sparky to the method and output their medical condition. In this section on class constructors, we'll start by reviewing how to write constructors for standalone classes when we aren't considering class inheritance. So first, what is a constructor? A constructor is a series of instructions that run when you create a new object. In essence, they construct the data in the new object. A constructor only runs when we create a new object. While not methods, constructors behave similarly to non-static methods. Let's look at this example. We start with a robot class. It has a class variable, robot count, and an instance variable, name. Here's our constructor. Constructors are usually public. The constructor's name must be exactly the same as the class name. A constructor must not have a return type. In this case, there are no parameters in the parentheses. The first line adds 1 to robot count. Each time we create a new robot object, robot count increases by 1. As a class variable, there is only one shared copy of robot count, so we can use this variable to keep track of how many total robot objects have been created. The next line calls the random name method. The random name method generates a random number from 1 to 3 and sets the instance variable name to either Bender, HAL9000, or Gort. As an instance variable, each robot object has its own copy of the name variable. Now let's look at the space station class. In the main method, we declare a variable of type robot called x1. We set x1 to point at a newly created instance of robot. Creating the new robot object causes the robot class's constructor to run. Robot count is updated to 1. The random name method assigns the string to the name instance variable. The same thing happens with x2 and x3. Next, let's look at another class that has overloaded constructors. A class with overloaded constructors has 2 or more constructors, and Java chooses which one to call based on the number, type, or order of parameters. Now, let's look at the Solaria class. On the first line of the main method, we declare an Android variable, z1, and initialize it with a new Android object. There are no arguments passed, so Java uses a constructor with no parameters. On the first line of the constructor, we use the this keyword. In this context, this is referring to the current object, and it's calling another constructor in the same class. In the parentheses, we are passing one string argument. Java will find a constructor in the same class with one string parameter. The string literal R Daniel Olivois gets passed to the parameter new name. The name field is set to the value of the new name parameter. And the admin password field gets set to the string literal ABC123. Now to the second line of the main method. Here we pass one string to the constructor. In this case, Java goes directly to the second constructor when creating the new Android object. Let's look at a situation where overloading constructors causes problems. The class ConfusedRobot has two constructors. Each constructor has a string parameter, followed by an int parameter. The fact that the parameters have different variable names is irrelevant. Now on to the main method in the Floating City class. We are creating a new ConfusedRobot object and passing it a string, followed by an int. Java has no way to determine which constructor we want to call. For this reason, we would get an error if we tried to build the ConfusedRobot class. Let's look at a final example. We see that the RoboCop class doesn't even have a constructor. In cases where the programmer doesn't write any constructors, Java will give us a freebie, no parameter constructor. Remember, we only get this freebie if there are no other constructors, and it will always have no parameters. For the time being, we can think of the body of this constructor as empty. Now, let's look at the Detroit class, which contains a main method. Detroit will also get a freebie constructor, but in this case, we don't really need to think about it. Running the main method in Detroit won't create a Detroit object. Since we aren't creating a Detroit object, no constructor in the Detroit class is ever called. Frequently, we don't create objects from classes that contain main methods. In the main method, we declare a RoboCop variable named Alex Murphy and initialize it to point at a new RoboCop object. There are no arguments passed, so Java calls our freebie no parameter constructor. Since we haven't specified values for our fields, they will initialize to their default values. Now, let's suppose instead of having no arguments in the parentheses, we have an int argument. In this case, there is no matching constructor, so the Detroit class will generate an error when we run it. To fix this, we either need to write a constructor in RoboCop with an int parameter, or remove the int argument from the parentheses. Next, we'll learn how constructors call constructors in their superclass. Here are 4 important things to know about constructors for this lesson. Every class must have a constructor. Every constructor must call a constructor in its superclass. Constructors are never inherited. The Java compiler will sometimes write missing constructor code for us. Let's look at this vehicle class. The vehicle class doesn't explicitly extend any other class. However, implicitly it extends the Java object class. While I've never seen it done, technically you can write extends object. Looking at the vehicle class, we see it has 3 constructors. Suppose that somewhere else in the program, we declared a vehicle variable and initialized it to a new vehicle object. We aren't passing any arguments, so Java looks for a constructor with no parameters. Every constructor must call a constructor in its superclass. In this context, super calls the no parameter constructor in the object class. The object class's constructor runs and sets up its portion of the new instance. Now let's look at another example. Here, we declare a different vehicle variable and initialize it with another vehicle object. In this case, we are passing one string argument, so Java looks for the constructor with one string parameter. In this context, the this keyword is used to call another constructor in the same class. There are no arguments inside the parentheses, so Java looks for the constructor with no parameters. This top constructor has the super keyword, so indirectly, the middle constructor is calling a constructor in the object class. Once we are finished with the call to the top constructor, we finish up the code in the middle constructor. Finally, let's look at this third example. Here, we have a string argument followed by an int argument. Java finds a constructor with a string parameter followed by an int parameter. We see that there is no call in this constructor to a constructor in the superclass. In this situation, Java will insert a call to a no-parameter constructor in the superclass. For this to be successful, there needs to be a no-parameter constructor in the superclass, which in this situation there is. In situations where the superclass doesn't have a no-parameter constructor, you can't depend on Java to insert the call for you. Let's look at another variation of this class. Here, there is no constructor at all. Java will start by inserting a generic no-parameter constructor for us. Next, it will add a call to a no-parameter constructor in the superclass. Let's look at these three classes. The vehicle class is implicitly a subclass of object. Airplane is a subclass of vehicle, and F-16 is a subclass of airplane. There is only one constructor in vehicle. The constructor doesn't have a call to the superclass, so Java inserts one. Airplane has two constructors. The first line calls the constructor in the superclass and passes a string followed by an int. Those arguments get passed to the matching constructor in the superclass. The second constructor has a call to a superclass constructor and passes no arguments. This will generate an error because there is no matching constructor in the vehicle class. We need to modify this call to pass a string followed by an int so it will work with the available constructor in the superclass. F-16 doesn't have any constructor at all. Java writes a basic no-parameter constructor. The basic no-parameter constructor includes a call to a no-parameter constructor in the superclass. Remember, Java only creates a simple no-parameter constructor for us if there aren't any other constructors in the class. Finally, we'll learn how constructors send information to their superclass. As we learned earlier, every constructor must call a constructor in its superclass. Often these calls are used to pass up important information to the superclass. Let's look at the class Ghost and its subclass Slimer. Ghost has two instance variables, also known as non-static fields, a string color and a boolean isScary. In the constructor, we don't explicitly make a call to the superclass's constructor, so Java will automatically add a call to a no-parameter constructor in the superclass. We notice that we have a field named color and also a parameter named color. These are two separate variables that happen to have the same name. Also, there's a field isScary and a parameter isScary. If we don't specify which one we're referring to, Java will assume we're talking about the parameter. We can use the this keyword in either constructors or non-static methods to specify that we're talking about the field in this object. Next, we'll look at the subclass Slimer. Slimer has an instance variable, boolean isHungry. Slimer's constructor has two boolean parameters. The constructor starts by calling the superclass's constructor. All Slimers are green, so we simply pass up the string literal green. Next, it passes the value of the variable isScary up to the Ghost's constructor. Finally, it sets the field isHungry to the value of the parameter isHungry. Now we'll trace some code and see how the constructor builds the object in memory piece by piece. For the purpose of this tutorial, we'll assume that the code we're writing is in a main method somewhere. We start by declaring a reference variable, Sam, of type Ghost. The variable is placed on the stack and is currently uninitialized. Next, we will initialize Sam with a new instance of Ghost and pass the arguments white and true to the constructor's parameters. The constructor calls a no-parameter constructor in the object superclass. We don't need to worry about what the constructor in the Java object class does. Now, we set the instance variable color to the value of the parameter color. We see the value of color updated in the object on the heap. We set the instance variable isScary to the value of the parameter isScary. The parameter held the value true, which was copied to the instance variable and shows up in the object on the heap. We've finished the declaration and initialization of the Sam variable. Next, let's create an instance of a Slimer. We declare a reference variable Sue of type Slimer. Sue is initialized as a new Slimer and is passed the arguments true and false, which go to the parameters isHungry and isScary. The first thing we do is pass up to the superclass the string literal green and the value in the parameter isScary. In the superclass Ghost's constructor, we call the constructor in the Java object class. Then we set the field color to the parameter color, which was passed up as green. Next, we set the field isScary to the value of the parameter isScary, which was passed up as false. Both of those values end up in the object on the heap. This object has two parts that we are concerned with. The top part is in the ghost part. The bottom part is in the Slimer part. We see a line separating the two portions of the object on the heap. Now that we've finished running the constructor in Ghost, we can pick up where we left off in Slimer's constructor. The parameter isHungry was passed a value of true. We set the instance variable isHungry to the value of the parameter isHungry. We see the updated instance variable is reflected on the object on the heap. We end up with two reference variables on the stack, Sue and Sam. The reference variables are each pointing at an object on the heap. You're at the end. Tell me in the comments, was the pace of this video too fast, too slow, or about right? Check out the other resources on the channel, and I'll see you soon.